Hi, welcome to Displacement, Velocity, Acceleration, and Time. 1D motion, not one direction, as in the boy group, but one dimension. So we actually have two directions, to and fro, up and down, left and right, but in one along a line, one dimension. So let's think about what these terms really mean. Displacement really is how far have we gotten? This can be positive or negative. We can define that however we like. Typically, if we have some sort of a line, we might say that if this is our starting point, this would be a positive direction, this would be a negative direction. You can do whatever you want, up, down, if it's an angle, you define it whatever makes the most sense for you and your problem. Velocity is, well, how fast? How do we measure that? And velocity, remember the V in this case, helps us remember that it's a vector quantity, so it's a direction. So this would be measured how far in what time. So basically we have to go where how far displacement might be measured in meters. Velocity would be how far divided by how long it takes us. How much time? Or meters per second, if we're going to use a, kind of a metric kind of thing. Now acceleration, that's a little trickier. That's how fast are we changing our velocity. So this would be measured in meters per second, that's our velocity, divided by how many seconds. So meters per second, or if we're talking about in the United States, it should be like miles per hour per second, let's say. So 0 to 60 in 1 hour, not very impressive. That would be 1 mile per hour per second. But in our case, we're going to stick with the metric system. And through the magic of arithmetic, we can say that this is equal to meters per second squared. Because divided by second 2 times gives us divided by second squared. All right, so here's a graph. Let's kind of move things around and see what's going on here. Let's sort these 4 terms need to go somewhere. First, we added label our graph. We're almost always going to have time on our horizontal or x-axis. In this case, we could have displacement, acceleration, or velocity. In this case, all we have is displacement, and that oftentimes will go onto the y or vertical axis. Okay, now, so this is displacement in meters, and you really should have, this will be in meters, and time should be measured in seconds. You really should indicate what units you're using on your graph. So, as time moves, we see displacement here. Meters changes. So where is it moving? So let's see, moving would be here. I don't want that part, I'm going to erase that. Moving, definitely here, because it's changing its displacement over time. What's happening over here? It's stationary. What about over here? Oh my gosh, it is still moving here. And guess what? It's moving over here too. Something's different though, huh? We've got some interesting stuff going here. We're going to talk about the slopes of graphs and what they mean. A couple things. Do we have a positive slope or negative slope? Here, oopsie, in this section we have a positive slope. In this section here, we have a 0 slope. Here, in this section, we have a negative slope and also a negative slope. Different values though. This is a little steeper. So that indicate that we're moving backwards, whatever we define our negative direction to be, at a higher velocity or speed than over here. All right, let's see what we got. So what's going on? Well, we have a constant positive slope. So this would mean that we're going at, this is a constant velocity. constant velocity because it has a constant slope in the distance versus time graph. In fact, we can go forward, we can go a little more, and we can say, well, how fast are we moving here? Well, we're moving the positive direction, given that we are going, we have a positive slope. And let's just pick some points. How do we get meters per second? Well, it's a slope, y over x, or distance per time, meters per second. There we go, awesome. Let's just pick a point, constant slope, so it doesn't matter where we pick. This would be 2 meters starting from here. So from here to here, we've gone 2 meters in 2 seconds. Or really, that's just 1 meter per second. So not so bad. Oh, what's going on here? This versus time, our slope is changing. It seems to be positive pretty much in all places here. So this would actually be non-constant velocity. In fact, we would say this is accelerated motion, because acceleration is just a change in velocity. So accelerated motion. Really do like this feature because my handwriting is not very good. So how could we figure out what the velocity is? It would be a question of just find the slope. So meters per second, y over x. So how do we do this? Well, we'd have to, because the slope is changing everywhere. This is actually why Isaac Newton and Leibniz invented calculus. We don't have to deal with that. We can just think about this qualitatively. So what does this look like? Well, the slope here is sort of like here. Officially, we're drawing a tangent to this, but basically we got the idea. We're getting steeper and steeper and steeper as we go. So what we can tell is that the velocity here, the slope is much steeper, so we're going much faster here. So this represents the here, slow, faster, faster, faster. And so this would be accelerated motion. In fact, we would say that this is a positive acceleration because the velocity is increasing over time. So let's see what we do. I grabbed this out of our textbook, Hewitt. So let's see what's going on. Velocity versus time. This is a little different. Notice that before we've been talking about distance versus time or displacement. And we can kind of use those synonymously. Now, if velocity is changing, that must mean that in this section, the velocity has a slope. So that means we must be speeding up. Now B, zero slope in the velocity. Are we moving? Oh yeah, we are. 20 meters per second apparently. But we're not changing that, so we're not accelerating. We're at a constant velocity. In fact, it's a positive velocity, so if we're going left, right, we say we're moving to the right. Here, negative slope. So that means our velocity is decreasing. In fact, it's going from 20 over here down to 0. Are we moving here? Well, yes, we are. Are we moving backwards because of negative slope? No, we're moving positive. This is all positive 20 meters, 19, 18, 17, 16, 15, etc. until we come to a stop right here. So to recap, in region A, the object moves with constant acceleration, which means we're having, its velocity is changing. In B, the object is moving with constant velocity. So what's acceleration? 0, because it's not changing. In C, the object is moving with constant acceleration, which means we're changing, but comparing this region with this region, notice the slopes are different. Two things. This is a negative slope, this is a positive slope. This is steep, this is relatively shallow. So the acceleration is slower because the slope is less steep. And we can tell that acceleration is negative because the slope is negative or downwards, you could say. So let's think what's happening here. Let's fill these in. So if we start with the zero velocity and then the velocity changes, what happens to that position? Remember, it must be a curve because we're accelerating. So what's going to happen is the position is we're going to start moving, but we're going to start moving faster and faster and faster. And then what happens? we're moving at a constant velocity. So does our position change? Sure, we're moving. And it's at some slope, which represents the velocity. That's kind of a tough one. Now what's going on here? Velocity is decreasing, decreasing, decreasing. At some point it's zero. What does that mean? It means we're stopped. So the position, well, we don't really know where we started, but let's say that we started zero. And let's see, we're moving really quickly, but now we're kind of slowing down, slowing down, slowing down, slowing down. Wait a minute, but our velocity is negative now. That's interesting. What does this look like? It looks like maybe a ball you throw up in the air or something. And this, so let's keep that in mind. And notice that the velocity being zero doesn't mean we're back at the beginning. It means that we're moving, that we've just stopped moving for a second, and then we're starting to go down again. So it's acceleration. Let's see, that was meters per second divided by seconds. So again, it's the slope, y over x. So we can just pick a couple points, 0, 0, 55. So let's see, we want meters per second divided by seconds, or y over x. So let's go, we've gone from 0 to 50. So we've increased our velocity by 50 meters per second, and it's taken us 5 seconds, or 10 meters. Now I'm going to use that shortcut we talked about, meters per second squared. Oops, did I do that right? No, I did not. Someday I really should learn how to divide. Actually, I did get that right. I'm sorry. Moving on. Okay, so let's see. What object has an acceleration of 0 meters per second per second? What would that mean? The velocity is not changing. It's got to be C, which has a positive acceleration. So that would mean our velocity is increasing over time. It would be D and B. So let's kind of review. We have a displacement versus time. Now, it's very important to keep track of what are we talking about versus time? Displacement, velocity, or acceleration? So displacement, we have a constant positive velocity because we're going meters per second. That's our velocity. It's positive. We're not changing velocity, but it's a positive velocity. That means we're moving. Or sorry, the displacement, we're not changing the displacement at all. So we are actually stationary. Now we are moving here, so we have a velocity, but the displacement, we're going backwards. So that must be a negative velocity. And as we move down here, we have a constant negative velocity as well, which means I'm actually going backwards, where we're left of where we started. But the rate at which we're changing velocity is less. Here, flat means we're stationary. And now we've got some increase, faster, 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 and then we finally stop. Over time means we've come back to zero, we're back home essentially. Notice that these above the axis, positive direction, that means we're, I guess, farther from where we started, and negative direction means we're behind where we started. So negative acceleration, velocity changing, negative, it's got to be A. Let's see, largest to smallest. So largest would be the steepest. Looks like B is the steepest positive. D is next, and then negative, if we're ranging. So B is bigger than D, is, I'm sorry, D, I said. So let me erase that. It's bigger than D, and then we have C, which is 0, and then we have a negative acceleration with A. So positive velocity values always show forward velocity, no matter what the slope. Negative velocity values show negative velocity, no matter what the slope. So where are we moving forward? Remember, positive velocity means we're moving forward. So here, we're moving forward. Here, we're moving backwards. So anywhere we're above the velocity time, we're above that zero axis, we're moving forward. Are we stationary here? No, we have a positive velocity. We're still moving. We're not changing. We're not accelerating. What happens right there? We stop moving at all. We're stationary just for a moment, and then we start moving backwards. Backwards, do you remember what we just said? Negative values of velocity. Momentarily stopped, gotta be right there. So let's see. So if we add up all the distances that we go, if we kind of chop this all up, basically that's how calculus got born. But if we ended up getting the entire area under this curve, that will give us the displacement. Let's say it's a rectangle, so we're kind of doing we know how to do the area of a rectangle, right? It's length times width. Or in this case, this side is velocity, and this one's the time. So let's see. Well, what happens? So for area of a rectangle, it's length times width, or in our case, we've got velocity, which is meters per second, times second. Well, what does that get? These cancel out. Put a 1 under there if it makes you feel better. These cancel out. That gives us meters. Hey, that's cool. So to find the distance from a velocity time graph that an option has moved, we just multiply y times x, velocity times time, we get the distance. So let's see, what's the displacement? Well, we basically want the area. Uh-oh, tricky, we've got a triangle. Anybody remembers how to do this? Area of a triangle was, well, it's half a rectangle is just length times width, or triangles, we could call it base times height. And triangle is basically half a rectangle. All right, well, let's check out what we got here. So we've got the distance traveled. It's 1/2 because it's a triangle. And let's see, the base would be 4 seconds times, and this represents 40 meters per second. Meters per second. Hey, look at the units. Again, seconds cancel out. 4 times 40 is 160. Half of that is 80. 80 meters. Did I get it? Yes, I did. So let's see. What's the acceleration at a constant velocity? Constant velocity, not changing velocity. 0. What if I'm at rest? 0 again. When is it? Well, maybe it's not. What if I'm at rest? Try to think of one. We'll pick this up at some point. So basically, these are all the various ideas that you can have between velocity, acceleration, and displacement. A lot of times, I like to do what we call stacks of graphs. And basically, I like to put graphs on top of one another. All of them. I like to have time on the bottom, typically in seconds, could be something else. And then I'm going to have 3 different graphs. I'm going to have, this will be acceleration. And again, hopefully by now it's starting to become familiar that it's meters per second squared. We have velocity, which is our change in position versus time. Meters per second, plain old second, not squared. And displacement or position. And that's just measured in meters. Notice what happens when we go down the stacks of graphs. We start with displacement in meters. We divide by second. And we divide by second again. We get acceleration. We could keep going. In fact, they call this jerk, snap, crackle, and pop if we were to do 4 more graphs. But there you have it. Go look in the textbook and the readings on the physics classroom, and hopefully this will make sense. If you have any questions, please do post in the Ask a Question, or you can send me an email. Thanks and good luck.